Chapter 22, Physics for Biology and Medicine Students, East African Literature Bureau Services. Chapter 22, Electrostatics. Chapter 22.1, Introduction. From early times it has been known that if amber is rubbed with fire, the amber acquires the ability to pick up small pieces of dust or paper and show other unusual phenomena. The same is true if glass is rubbed with silk or if hair is combed smartly with a dry plastic comb. Further, if the amber, so electrified as it is called, is touched again, a light metallic ball suspended from a silk fiber and a similar electrified ball on a silk thread is brought up. The two electrified balls repel each other. However, if a ball touched by electrified amber is brought near a ball touched by electrified glass, the balls no longer repel but attract. It would appear therefore that there are two types of electrification, which we call positive and negative electrification. A more detailed investigation shows that although the amber carries a negative electric charge, the fire with which it was rubbed shows a positive charge, and that rubbed glass shows a positive charge, although the silk with which it was rubbed shows a negative charge. Very detailed investigation will show that in each case the positive and negative charges produced are equal in magnitude, which is a particular case of the principle of the conservation of electric charge. Charge can neither be created nor destroyed, although it may be neutralized. If this phenomenon is further investigated, it is found that rubbing will produce electric charges in almost any pair of substances used, although in certain cases it is necessary for reasons which will appear later to be very careful about the conditions, or the phenomenon may not always be observed. It will therefore appear that all substances normally contain positive and negative charges in equal amounts, since all substances are normally electrically neutral. One or other of these charges, in fact the negative charges, can be removed fairly easily by frictional effects. In that case, the substance which has acquired the negative charge from the other becomes negatively electrified, and the second substance, having lost some of its negative charge, is now left with a surplus of electricity and shows positive electrification. In this case, I am investigating and documenting my electrical reaction to thunder and lightning, and the weather, and how I conduct static electricity like thunder, and how my body and my system reacts to thunder by thunder, and how I thunder back, how I perceive the electricity as thunder in my body as static electricity, and I'm using these electrostatics to study the thunder and my conductance and my low resistance to electricity, my resistance threshold, and my potential, my impedance, the potential difference, and the conductance, of my conductance to electricity. How much electricity can flow through my body at a given a specific time or a specific situation or specific circumstance, and how I react back, and how much electricity I can conduct through to other elements, or back to the source of electricity. As will be seen in the chapters on modern physics, the Bohr-Rutherford theory of the atom envisages it as consisting of a central nucleus of small size, about 10 power 30 centimeters in diameter, which contains most of the mass of the atom and all of the positive charge, surrounded by a cloud of electrons which travel around the nucleus in circles and ellipses of approximate linear dimension of 10 power minus 8 centimeters. These electrons are very light. Each has a single negative charge, and there are many electrons as there are positive charges on the nucleus, but the atom as a whole is electrically neutral. The electrons nearest to the nucleus are very tightly bound to it in enclosed shells, as they are called. An atom which with from 2 to 10 electrons has the first two tightly bound in a closed shell. Atoms with more than 10 electrons have the first two and the next 8 bound tightly in closed shells, and so on. The electrons outside the closed shells are fairly loosely bound to the atoms, and it is these which can be wrapped off. It is also these which produce the optical spectra of the atoms and the part in chemical bonding. The charge of each electron is found to be, as we shall see later, minus 1.6 times 10 power 19 coulomb. Chapter 22, Conductors and Insulators. If a rod of glass is held in the hand, wrapped with silk, and then brought up to an electrified ball on a silk thread, the ball is repelled or attracted. If the same is done with the metal rod, the ball is unaffected. On the other hand, if the metal rod is held in a glass, handle and the experiment is repeated, movement of the ball results. One is led to believe that the electric charge can move about on the metal rod and can flow into or through a human body, but that it is not so in the case of the glass substances. On the other hand, if one is led to believe that the electric charge can move about on the metal rod and can flow into or through a human body, but that is not so in the case of the glass. Substances are therefore divided into cases: conductors, such as the metal rod, along which charge flow can flow or be conducted, and insulators, along which charge cannot flow. In conductors, some of the electrons are conduction electrons, which are not bound to any atom but can move about relatively free in the structure. In insulators, the electrons tend to be bound to individual atoms and do not have this ability to move about in the substance as a whole. The dividing line between conductors and insulators is not a sharp one. In this region are the substances known as semiconductors, which have become increasingly important in recent years. Semiconductors alter their ability to conduct markedly with temperature, impurity, and etc. This change in conducting properties is what makes semiconductors so important. CF sections, chapter 33.2, 33.3, and 33.4. Charging by induction, chapter 22.3. If a positively charged rod is brought close to a metal object which is uncharged, the electrons in the object are attracted towards the rod and tend to accumulate in the portion of the object nearest to the rod. The opposite of the object is then positively charged, since there is a deficiency of electrons of that at that place. This phenomenon of induction can be used to check the object, for it is attached to the ground or to a large conductor. Electrons which flow to the ground attracted to the surplus positive charge. An alternative way of looking at this is to say that the object now consists of itself and the earth. Electrons are attracted to the part of the object nearest to the charged rod, leaving an excess of positive electricity at the other side of the composite body, i.e. on the earth. If the connection is now broken and the charged rod is then removed, the object retains the electrons which it has acquired from the ground and shows negative electrification. The opposite effect is produced if a negatively charged rod is brought up. If the object is not connected to the ground, the positive and negative electric charges redistribute themselves over the object when the rod is removed to produce electrical neutrality. Note that while the rod is close to the object, the two will be attracted to each other. The force of attraction between the positively charged rod and the negative charge at one end of the object is greater than the force of the repulsion between the rod and the positive charge on the other end of the object, since the latter is further away. It should also be noted that electric charge does not, in general, distribute itself evenly over the surface of a conductor. It is most dense where the curvature is greatest, and therefore tends to be concentrated at any pointed portion of the surface. If indeed there is a sharp point on the surface, the density of the charge may become so great that the air molecules striking it acquire charge from the point and are instantly and violently repelled. A noticeable wind can be felt near the charge point. The action of a lightning conductor depends on this fact. A lightning conductor has a collection of points at its topmost end, and the other end being grounded. Clouds, particularly those with turbulent currents in the interior, are often charged, usually negatively on the base and positively at the top. There is a danger that they will discharge by a lightning stroke to Earth. When such a cloud passes over a lightning conductor, induction takes place, positive charges being induced on the points on the conductor. Positive charges spray upwards because of the wind effect and mentioned earlier. This tends to neutralize the negative charge on the base of the cloud and prevent a lightning discharge. Even if this desirable effect is not achieved, any discharge that takes place is likely to go along the track of the light positive charges. Buildings in the vicinity of the conductors are thus protected. Chapter 22.4 Coulomb's law. It is obviously necessary to introduce some quantitative measurements in the subject. It is necessary to have available collection of the rectified bodies, the ratios of the charges on which are known. This can be achieved by acquiring a collection of identical metal balls on insulating handles and charging one of them. This ball, which will then possess an electric charge of unknown magnitude Q. If the ball is tied to another from symmetric considerations, it will be realized that the charge will be shared equally and that each ball will now possess a charge Q/2. If one of these balls is tied to an untied ball, each of them will possess a charge Q/4. Hence, one can, in like manner, obtain charges of magnitude Q/8, Q/16, etc. Further, if one touches balls containing charges Q/2, Q/4, each will contain a charge of 3 Q/8. If one touches balls containing charges Q/2 and Q/8, one can obtain charges of 5 Q/16, and so on. It is thus possible to prepare a series of charge balls containing charges of